Welcome to the lecture series of signals and system. Till the previous lecture, we have seen almost all the important properties of the Laplace transform, and we completed some important examples to express the use of those properties more. In this lecture, we will include final and initial value theorems based on the examples based on the final and initial value theorems, and also we will include some examples related to the Laplace transform, and if time permits, we will go to the solution of the differential equations by using Laplace transform. So first, we will include some examples based on the initial and final value theorems of the Laplace transform. Then we will go to the inverse Laplace transform. The first example in this context says that the Laplace transform of xt, which is x of s, is given as 4 upon s square plus 3s minus 5. And another example says that the Laplace transform of x of t, which is x of s, is expressed as 3s plus 2 divided by s into s square plus 3s plus 2. So this is 3s plus 2 divided by s into s square plus 3s plus 2. And by using this Laplace transform, we have to get the initial value of the signal in time domain. Means we have to get the x of 0. And from the initial value theorem, we know that the initial value of the function x of t, where t tends to 0, can be expressed in the form of Laplace transform as limit s tends to infinite s times x of s, where x of s is the Laplace transform of the given signal xt. The Laplace transform of xt is given as x of s. So to find the initial value of the given function, first we have to multiply with s in this Laplace transform and then put the value of s is equal to infinite. We will get the initial value of the function. So x of s in the first case, x of s is given here is 4 upon s square plus 3s minus 5. So I will write x of 0 as limit s tends to infinite s into x of s, and s limit s tends to infinite s into x of s is given as 4 upon s square plus 3s minus 5. To put the value of s equal to infinite in this equation, first we have to divide numerator and denominator by the highest power of the denominator. So the highest power of the denominator here is s square. That means we have to divide numerator and denominator by s square. So on dividing numerator and denominator by s square, we will get x of 0 is equal to limit s tends to infinite. This will become 4 by s upon 1 plus 3 by s minus 5 by s square. Now here I can put the value of the limit as s is equal to infinite in this case. When we will put s equal to infinite, this will go to 0, 4 by infinite will go to 0, this will go to 0 and this will go to 0. So this will become 0 by 1, which is equal to 0. It means that the initial value of this function will be equal to 0. We can find it by using initial values we know. Also, By using the same concept, we can find the initial value of the function whose Laplace transform is given in the second case. So, in the second case, to get the initial value limit t tends to 0, x of t will be equal to x of 0. I can write it as this will be equal to limit s tends to infinite s times x of s. We can write it by using initial value theorem. So the value of x of s here is s into this is 3s plus 2 divided by s into s square plus 3s plus 2. Again, to put the value of limit here, we will divide both numerator and denominator by the highest power of the denominator, or we can say highest power in this equation. So the highest power here is it is s cube. It means that we have to divide in the denominator and numerator by s cube. So on dividing numerator and denominator by s cube, we will get x of 0 will be equal to limit s tends to infinite s into, I will multiply in it, this will become 3s square plus 2s divided by s cube upon s cube plus 3s square plus 2s divided by s cube. I can write it in this way. This can be further simplified as limit s tends to infinite. When we will divide with s cube, this will become 3 by s plus 2 by s square upon 1 plus 3 by s plus 2 by s square. Now we can put s equal to infinite here. So this will become 3 by infinite, this is 0. 2 by s is 2 by infinite is 0, this is 0, and this is also lead to 0. So this will become 0 by 1, which will be equal to 0. In this case also, the initial value of the given function will be equal to 0. Now the next example says that find x of infinite if x of s is given by, means we have to get the final value in the next example. So the next example here is find x of infinite if x of s is given as, the first example is 1 upon s minus 4. X of s is equal to 1 upon s minus 4. The second example says x of s is equal to s minus 2 upon s into s plus 4. S minus 2 upon s into s plus 4. The third example is x of s is equal to 2 upon s square plus 3. 2 upon s square plus 3. And the fourth one says that its says that x of s is equal to 2 upon s square plus 4s minus 2. 2 upon s square plus 4s minus 2. In all these cases, sorry, in all these cases, we have to get the final value of the given signal in the time domain. So, in the first example, we will look what is the final value theorem is. So, the final value theorem says that if Laplace transform of x of t is described by x of s, then the final value of x of infinite can be found by using this relation as x of infinite is equal to limit s tends to 0 s into x of s. Here limit s is tending towards 0. So I will put value of s equal to 0 in this relation s into x of s. The first question says that x of s is given as 1 upon s minus 4. So x of infinite will be equal to s times limit s tends to 0 s times x of s, or this can also be written as limit s tends to 0 s into value of x of s is 1 upon s minus 4. This is 1 upon s minus 4. So from here, if we will put s equal to 0 in this relation, we will get final value of this function, this signal will be equal to 0. But one condition is there. To apply the final value theorem, the pole of the S domain should not lie in the right half of the S plane. Here S equal to 4 will lie in the right side of the S domain. So the system is unstable and we cannot apply the final value theorem. If the pole lies in the right side of the S plane, in the right half of the S plane, we cannot apply the final value. So we cannot find the final value of this equation by using this relation. Consider the second one. It says that for the second, x infinite will be equal to limit s tends to 0 s times x of s, where x of s is given here s minus 2 upon, this is limit s tends to 0, x of s is given as s minus 2 upon s into s plus 4. This s and this s will cancel each other. Now I can put the value of s equal to 0 in this equation, and this will become minus 2 by 4, which will be equal to minus 1 by 2. This will be the final value of the given relation in the example number 2. We can apply the same concept to find the final values in the example 3 and 4. So by using the final value theorem, we can find here the final value of this equation 3 as x of infinite will be equal to limit s tends to 0 s into x of s, and this will be equal to limit s tends to 0 s into x of s is given as 2 upon s square plus 3. So 2 upon s square plus 3. Directly we can put the value as s equal to 0, and this will become 0 by 3, which is equal to 0. So the final value of the equation given in example number 3 will be equal to 0. In the C part, 2 upon s square plus 3. But here, given that the final value of this x of t will be equal to 0, but here is we have to consider the position of the poles also. Always remember, when we are going to apply the final value theorem, we have to always check the position of the poles in the given relation. In the Laplace transform, here the poles will lie at s is equal to plus minus j root 3, and these poles will exist on the j omega axis. Means we can say it may be treated as marginally stable system, or in the signal system we consider it as unstable system. There is no concept of marginally stable. Marginally stable systems are studied in the control system only. In the signal system point of view, the given system will be unstable, and we cannot find the final value for this given system because poles are lying in the j omega axis, so there is no concept of the final value of this system. This system will not settle at any final value because poles are imaginary. It will keep oscillating and it will not get settled at any final value. The next one is x of s is given as 2 upon s square plus 4s minus 2. We have to get the final value of this given. So the final value x of infinite for the example number 4 can be given as limit s tends to 0, s times x of s square. X of s is given as 2 upon s square plus 4s minus 2. I can put the value of s equal to 0 directly in this relation, so this will become 0 by minus 2 will be equal to 0. So we can find the final value in this equation because you can check the poles will lie on the left side of the s plane. So we can find the final value of this given Laplace transform by using the final value theorem, and this will be equal to 0. Now consider and verify the initial and final value theorem by including one more example. And this example says that verify, find the initial and final values if they exist of the signal with Laplace transform given below. Find the initial and final values if they exist, where the Laplace transform is given as the first one is x of s is given as s plus 4 upon s square plus 3s plus 5. S plus 4 upon s square plus 3s plus 5. The second one is s square plus 3s plus 6 upon s square plus 2s plus 3. S square plus 3s plus 6 upon s square plus 2s plus 3. For this given example, we have to find the initial and final values of the given relation, but first we have to check the existence of the final value of the system. So in the first example, we can find the initial value by using the initial value theorem, which states that if the Laplace transform of x of t is x of s, then its initial value x of 0 will be equal to limit s tends to infinite s times x of s. So the initial value will be limit s tends to infinite s times x of s is given as s into s plus 4 upon s square plus 3s plus 5. Multiply with this s in the bracket, this will become limit s tends to infinite s square plus 4s divided by s square plus 3s plus 5. Again, we have to put s equal to infinite in this relation. For that purpose, we have to multiply and divide the numerator. We have to divide the numerator and denominator by highest power of the denominator, which is equal to s square. So this will become limit s tends to infinite. When we will divide with s square in the numerator, this will become 1 upon 4 by s upon 1 plus 3 by s plus 5 by s square. Now we can put the s equal to infinite in this relation, and this will become 1 plus 4 by infinite plus 1 plus 3 by infinite plus 5 by infinite. This will go to 0. This is 0 and this is 0. So the final value of the given signal will be equal to 1 as given in this example. This is the initial value, and to get the final value we will apply the concept of final value theorem. This will become initial value is 1 and final value will be equal to this s will tends to 0 to get the final value of the signal. So to get the final value, I will use this relation x of infinite will be equal to limit s tends to 0 s multiplied with x of s, and this can be written as x of infinite will be equal to limit s tends to 0 s into x of s is s plus 4 upon s square plus 3s plus 4. This will be equal to, we can directly put s equal to 0 in this equation. This will become 0 by 5, which is equal to 0. It means that the initial value for this given signal will be equal to initial value will be equal to 1 and final value will be equal to 0. Apply the same concept to get the final value in the second example. The final value means x of infinite will be equal to limit s tends to 0 s times x of s, and this will be equal to limit s tends to 0 s times x of s means s times s plus 4 upon s square plus 3s plus 1. No. In the second example, x of s is given as s square plus 3s plus 6 divided by s square plus 2s plus 3. This is the second example in which x of s is given as s square plus 3s plus 6 divided by s square plus 2s plus 3. I can put the value of s equal to 0 directly in this equation, and this will become 0 by 3. This is equal to 0. So the final value for this given given example will be equal to 0. And to get the initial value, we will apply x of 0 will be equal to limit s tends to infinite s into s square plus 3s plus 6 divided by s square plus 2s plus 3. Now, to put s equal to infinite, we have to divide in the numerator and denominator by highest power of s, and this is equal to s cube. So this will be equal to divide with s cube. This will become limit s tends to infinite s square s cube plus 3s square plus 6s divided by s cube upon s square plus 2s plus 3 divided by s cube, and this will become equal to 1 plus 3 by s plus 6 by s square divided by 1 by s plus 2 by s square plus 3 by s cube. And when I will put s equal to infinite here limit s tending to infinite. When this will tend to infinite, this will become 0, this will become 0, and this will also become 0. So the initial value itself is going to infinite for this relation. Whereas final value have some finite value, but initial value is going to the infinite. This is why we can say the initial value of the time function will not exist, because if we will take the inverse Laplace transform in this relation, we will get a term. When we will take the inverse Laplace transform of this relation, we will get delta t. So the initial value for this function will not exist. The next example is based on again initial and final value theorem. We have to verify the initial and final values in the time domain also. So the next example here says that verify the initial value theorem for the following functions. Verify the initial value theorem for the following functions. Verify the initial value theorem for the following functions, and these functions are x of t is given as 4 minus 2 times e power 3t. 4 minus 2 times e power minus 3. The second one says that x of t is given as 3 into e power minus 5t. 3 into e power minus 5t. Here this is plus 4 minus 2 into e power 3t. So we have to verify the initial value. Means first we will get the initial value of the signal in time domain itself by putting t equal to 0. So here limit t tends to 0, x of t will be equal to x of 0, which is equal to 4 minus 2 into e power 0, which is equal to 2. But I will put t equal to 0 here. This will become 4 minus 2 into e power 0. So this will be equal to 2. This is the initial value of the signal in the time domain itself. But by using the property in the Laplace transform initial value theorem, we can write limit t tends to 0 x of t as limit s tends to infinite s into x of s. So first we have to calculate x of s by using this relation, and if xt is given as 4 minus 2 into e power 3t, then x of s will be equal to Laplace transform of 4 will be equal to 4 by s minus this will be equal to 2 upon s minus 3. This is the Laplace transform of the given equation 4 by s minus 2 by s minus 3, or this can be simplified as s into s minus 3 4s minus 12 4s minus 12 minus 2s. So if we will put the value of x of s in this relation, this limit t tends to 0 x of t, which is equal to x of 0 will be equal to limit s tends to, this will be equal to limit s tends to infinite, because we are using the initial value theorem, and initial value theorem says that if limit t tends to 0 x of t will be equal to s tends to infinite s into x of s. So this will be equal to s tends to infinite s times value of x of s is this 4s minus 2s become 2s by s into s minus 3. This s and this s will cancel each other, and now we will divide both numerator and denominator by s. So this will become x of 0 is equal to limit s tends to infinite, here divide numerator and denominator by s. So this will become 2 upon 1 minus 3 by s. Now I can put the value of s equal to infinite in this relation, and this will become 2 by 1, which is same as we have seen earlier when we will put t equal to 0 here. In this case, when we will put t equal to 0 here, we will get 2. Also, this is verified by using initial value theorem. Move to the next case. have to verify the initial value for this given relation. From here, limit t tends to 0 in the initial value theorem, x of t will be equal to limit t tends to 0, 3 into e power minus 5t. When I will put t equal to 0 here, this will be equal to 3 into e power 0, which is equal to 3 itself. Now we have to find the initial value of this function by using the initial value theorem. So to get the initial value of this function, we will apply the initial value theorem as limit t tends to 0, x of t, which is equal to x of 0 will be equal to limit s tends to infinite s into x of s, and x of s here will be equal to 3 by s plus 5. So putting the value of x of s here, x of 0 will be equal to limit s tends to infinite s into 3 by s plus 5. Again, to put the limit s equal to infinite here, we have to divide the denominator and numerator by s. So this will become 3 upon limit s tends to infinite 3 upon 1 plus 5 by s. When I will put s equal to infinite here, this will be equal to 0 and this will become 3, which is again same as the initial value in the time domain, as it is analyzed by using the initial value theorem of the Laplace transform. So this covers almost all the important examples of the initial value and final value theorem in the Laplace transform. So this is all about this lecture. In the next lecture, we will find the examples of the inverse Laplace transform. Then we will use the property of the differentiation in the Laplace transform to get the solution of the differential equations by using Laplace transform very easily. So this is all for this lecture. Thank you.